My name is Peter Ritz, and I am the CEO at Fatbrain, and I'm here with my colleague Rajarshi Das, who's our Chief Technology Officer. And what we're going to talk about today is the cognitive solutions, but cognitive solutions which are auditable, explainable, fair, and causal, and how all these come together in the use cases. So at a very high level, we'll talk a little bit about the context and the background, the idea of what we call learned vector embeddings, and then auditability, explainability, fairness, causality, and policy learning, just kind of to tantalize everybody's appetite. Just a little bit of introduction about our business. We like working with IBM, and we think IBM's gear actually is perfectly set up for all the cognitive workloads, not only from a perspective of delivering the latest and greatest in the GPU-enabled technologies with power, but also some of the latest technologies that are coming down the pike with Q. So we'll use one example at least for how the concept that we have developed is generally applicable there as well, just by way of background. The problem that we're solving is very exciting for us, and it's a problem what we call the millennial data geometry. And the millennial data geometry problem is really one that takes us into the world of unstructured data from the world that we knew much earlier on, which is very difficult to manage in this three-layer cake, if you think about it. It's a very high end. It's the data geometry that's changing with social and with mobile and with all the unstructured interactions that are coming down the pike. A simple example is if you run a video, an advertising video on YouTube, the amount of data you get from one clip is going to break any one of your old systems just to kind of be able to track it. It's usually a 400 or 500 unit dimension array. And that's just not what you're used to if you're running Oracle or SAP or anything else to kind of do your earlier analytical workload on. At the bottom layer, you see the architectures, the application architectures, and how they have changed. And it goes from the early 60s artificial intelligence capable mainframes that could do handwriting to what you have today, which is cognitive and GPU native kind of things. And all of that with the journey of microservices is where we're coming to. And the middle layer is probably the most important one, and the middle layer really has to do with the fact that today's client expects hyper-personal experience because they're used to it from their kind of consumer applications, and it's very hard to do at scale. If you have 100 million customers or 30 million customers, it's very difficult to do that on a kind of personal level. So the big value that we see and a big problem that we solve for is this idea of automated learning versus feature engineering that normally is presented. And how do we take something that goes beyond classic analytics to cognitive analytics, which is much more valuable. And again, to us, the solution is very simple: a cognitive cloud in a box that comes to your data that enables this kind of an experience. This is just a little bit of a high-level view of what the differences between predictive analytics or just analytics versus the business AI automation experience is like. And the easiest example is, I'm old, so 15, 20 years ago, if you're out and if you were driving from point A to point B, you had to use a book to find your way there. And you had to open up that book, and you had to figure out where you were and how you kind of got there, and if you were kind enough and your wife allowed you, ask for directions. So that world is very different than everything that we know today, which is if you use any kind of navigation automation, whether it's Waze or Google Maps or anything else, if you veer off course, it's kind of telling you where you should go. So this idea of assisted decision-making and business AI automation where outcomes are learned and can be aligned to from what you're doing today. If you're using large and managing large amount of data with Hadoop clusters and everything else, that's great. You've counted it all. but have you learned from it? That's the big issue. And if you have 10,000 different things that you're counting, which 3 really make a difference? Right? 'Cause that's the hard part. That's the problem. So the things that we'll look at is we'll look at automated learning, and we'll talk about something, a special piece of technology we call learned vector embeddings. Learning the policy for how to make the real-time decision making. Being truly data agnostic. And what I mean by that is you should be able to use linear regression on the comments that are coming in from customer interactions. Well, there's one problem. To use linear regression on speech is not easy. But with our technology, you actually can. It's the same thing there are a lot of techniques in actually natural language processing that would be great to use on numbers. But unless you have some sort of a vector embeddings technology, it's very difficult to do that. So we have a way of dealing with all disparate sources of data, bringing it together and driving value out of that. We're domain independent, so what we learned in financial sector we can apply to pharmacy, pharma, we can apply to logistics and a bunch of other places. And probably the most important thing, if there's one thing you can learn about Fatbrain, is that we're auditable, explainable, and quantifiable. So if we help you make a decision, we can tell you why. We think that's a very, very big deal. Okay. This is a little bit of how the stuff works. So there's 3 simple steps. One step is simply connecting to the existing operational data stores. And the operational data stores could be as varied as literally social media, which is completely unstructured. This is Twitter, Facebook, YouTube, whatever. All the way on the other side, highly structured models which are regulated. Literally a model that you have running in a bank, or a model that's deciding whether to lend something or not lend on something, and so on. And all the core systems in between. So this example just shows off a situation where we're doing something for anti-money laundering, but the setup is very, very simple. Connect to all the data sources that are available, and that's kind of the first step. What we do when we connect to them is we learn through this idea we call LVE, or you'll hear me say alive. The LVE is this learned vector embeddings that understand and almost index the data. So we don't create another, from many data lakes, a whole other data set. We simply look at it as an index of learnings. So if transactional data had smiles and frowns, you can think of the whole thing as simply learning kind of the smiles and frowns of your transactions from that kind of a perspective. So that's what the learned vector embeddings is all about. The second step is kind of the engine that is able now to learn and use kind of the inferencing part of or recommendation part or imputation part based on this learned model, right? And then the last part is just making decisions. And again, this is a system that can be deployed to process billions of transactions that can distill into hundreds or sometimes even less than reports and investigations. So it can work at scale and learn very, very quickly, especially when it uses power. This is what kind of the collaboration workflow looks like. So it's a piece of software that gets deployed on gear in place. But the constituencies that it serves are engineering from a perspective of setting things up. So, connecting to data, you would not ask an analyst to do, but an engineer would do that. But an analyst would set up the KPIs across which they would want to see some sort of a business outcome. And the same thing for a owner of a line of business, right? An owner of a line of business would be the one who's kind of thinking through those issues. The folks who are vectorizing, segmenting, and analyzing from the previous slide would be analysts and data scientists. All of a sudden, as I mentioned earlier, a data scientist can use the same linear regression on unstructured data that she or he is used to using on all the numbers that they like so much. So all these things become enabled very easily in this setup. One of the interesting wrinkles that we have with our technology, not only can we look at unstructured data from a perspective of text and voice and a video and numbers, we can also look at structures, at graph data. So who talked to whom, or even source code or log files, or any of those kind of things are all in a realm of really good substrate for us to drive decision making. And then last but not least, if any of the decisions have to be audited or exposed to external regulatory bodies, we enable that as well. Every transaction and every decision that we make actually gets safe stored into a trusted source, which could be like blockchain, that could be exposed to that kind of a constituency. This is a little bit of the architectural deployment setup for us. So what you see in this quadrant here is a existing kind of workflow. You have a system of record. These are operational data stores. You know, we can take them on from Hadoop or just structured or unstructured things, as we mentioned before. And this is a normal workflow. And we simply enhance it through these two blocks, the orange block and the blue block, one for kind of learning and the other one for inferencing. Each of these run as a Kubernetes container, and they can scale magically, so to speak. And because they're running on cubes, they can be portable and deployed in hybrid infrastructures. So we like an infrastructure, for example, where it's GPU friendly on Power, but if a lot of transactional data runs on other architecture like IBM Z, well, that's great for us because we're able to do that in place and make it work really well. So just a little bit of context for that. If you're if you're a multi-cloud, we're friendly with that too. So that's just a little bit of a setup there. We're also fully API, RESTful API driven, so when this gets deployed in place, it comes up and it never leaves the prem, so to speak, in terms of its capability, its latency. All the really good networking innovation that's happened, and a couple of folks that went before us, whether it's from Mellanox or some of the other folks, would take advantage of all that to bridge this kind of latency gap, especially on-prem. You want to cover this a little bit?
So, so one of the key ideas that Peter mentioned about these learning, these vectors, the vector embeddings, is that typically, when people are data scientists are looking for trying to find a customer with a particular behavior, say the number of sales that they have done in the last 2 quarters. So they're comparing numbers to numbers. And so they can find that for this customer, these are the customers who are most like them. But as Peter mentioned earlier, imagine we not only have numbers associated with each customer in the system of records, but we also have additional system of records or data as to whom they have interacted with, perhaps a graph. We also have data with respect to each customer as to what they have said on the social media, which is text. And then the question becomes, when you have all these disparate types of data, how do you find out who is nearby to whom in the customer space? So this mechanism of figuring out these vectors, numerical vectors, gives us a common backplane to compute, to quantify the distances or similarities between customers. So if you have a customer that has just shown up, you can see that with respect to this customer, who are the nearby best customers? Or perhaps you have a best customer, and then you can quantify that who are the customers who are most like the best customers, to whom perhaps you should cross-sell, upsell, and provide discounts. So that's the key idea. But so this is the idea of in real time figuring out the digital twin, and then driving these to learning, not just in terms of actionable insights, but really learning outcomes, business outcomes. So a few minutes ago in the one of the other sessions on AI demystified, one of the aspects that comes across is deep learning and machine learning, and especially deep learning. These models are so complex that they can latch on to nuanced correlations that exist in the data. So for example, the example that was given was a deep learning system that is trying to identify between dogs and wolves. It turned out it was doing a good job in figuring out images of dogs and wolves, but it turns out for the images of wolves, it had latched onto the idea that in most images of wolves, there was snow in the background. So it was not that they had figured out what a wolf is, but it has latched onto another correlated attribute, correlated piece of data, in this case snow. And so it's going to be very critical going forward in terms of explaining the results. For each business decision that is made, can you explain why that decision was made? Quantify, in a quantified sense, explain, what are the factors that led to that particular decision. You don't want to say that, oh, it was because of snow that this is a wolf. That would be terrible. So similarly, business decisions, in some of our clients we're working with, fairness is a big issue. When you're approving loans, you want to guarantee that this approval process is not biased against sensitive attributes like race, sex, age, zip code. So you have to guarantee, in enterprise environments, you have to be able to guarantee that. And then of all the models that you're using in deep learning and in other systems, you have a plethora of models. They are interconnected and such. But unless you have a mechanism through which you can authenticate, you can verify and audit that this is the provenance of this model, this is the provenance of this business decision that was suggested, then it is likely to be vulnerable to attacks. So if you have made a series of decisions, then you can go back and say that this is the reason, this is the chain of custody of this particular decision, and these are the reasons for which a particular decision was made. So Peter is going to go through some of the examples that touch upon all these attributes, and we'll go from there.
It's really simple. And maybe one of the things that's most common to many of the businesses is this idea of the boogeyman of missing data. If I have to make a decision and 20%, 30%, sometimes 80% of my data is just not perfect for me to actually do the calculation or do something. It happens all the time, whether it's in banking and pharma and just a lot of fields. How do I deal with that? How do I fill the gap? And my choices are I'm going to throw stuff out, which then regulators find difficult, or I'm going to say, wait a second, I'm going to use the last value of what I had before, or I'm going to find some other way to fix the problem. So we have a principled way of fixing it that's explainable, fair, trusted, and so on. And it is able to perform 2 to 3 times better than the manual system that people deploy. So that's kind of a really interesting after effect of having this learned outcome system with live vector embeddings and the digital twin kind of capability. We're able to process, as I mentioned before, billions of transactions for anti-money laundering and financial fraud in per day, and then produce really impressive results in terms of very low false positive numbers. We can really uplift kind of cross-sell, upsell for folks. Like if I'm selling a mortgage and I want to sell an auto loan, how do I do that? Because just 1% or 2% lift is going to give me hundreds of millions of dollars normally, even if I'm a small bank, right? So it's a very interesting ability to do that, again, based on these kind of things. How do I drive much quicker customer interaction from a perspective of, everybody's been in a voicemail jail when you're, you have to say 20 things to get to the punchline, and it's just one sentence would do it if you really could do. Well, we can do that, and we can show you some of those kind of things. And then last but not least, for the pharma companies, they can't get paid until they ship a medicine and keep you on it if you need that special medication. Well, it takes so long to actually get that process through. And as Rajarshi mentioned, there's so many variables involved, usually literally hundreds and sometimes thousands of variables involved. It's very hard simply to say, oh yeah, I know which 3 knobs to turn to get that down, right? So, but we can help with that. Probably the most important thing I want to say today, in addition to auditability, is how fast we can deploy. If somebody's got 10 IFLs, we can have them up and running on Z. If somebody's got a power box with GPU, we can have them up and running very, very quickly. I mean, it's a very quick time to value from a perspective of getting engaged. And we think that's really a secret weapon at the end of the day, because shifting data to any other place other than where it is already is going to take you, forget governance, even if you bring in a Boeing, it's going to take you a very long time. AWS is this wonderful thing that will bring out a big semi-truck onto the stage and say, look, we can back up your data That's all great if you're doing it in one shot. You just won't be able to do it every second, and that's usually how fast the transactions are generating. So this just gives you a scale for why Amazon for itself has everything that it does behind its firewall. So that's just the way kind of the world works, right? This is a little bit of the things that Rajarshi touched on in terms of auditable, explainable, fair, and trustable decision making. If it's not quantifiable, it cannot be established to a regulator, it doesn't exist, right? So that's a very big deal for us, and we think in terms of AI going forward, if it doesn't have this, the city of New York already promulgated a regulation that you cannot make business-assisted decisions without auditability in place. So, and it's just the first, with all the privacy regulations in Europe coming on strong, we're sure that's going to be the case everywhere else as well. We talked about how fast we can start. Just a little bit of the use cases, I'll give you a flavor of that. So this is something we did for a bank on data imputation, and more specifically, this was a data set. It's a publicly available data set, so I can show it to you. Not the stuff that we did for the bank on their own stuff. But lots of different things that are in the Fannie Mae data. This all happened to be 2008 data because it's exciting things that were happening that year for banks. But you see there are different, this is just the shape of data on the left-hand side, and one of the things we're able to do is produce much better results even when we eliminate 25, 50, or 75% of the data and we impute that back in. And our curves, which are kind of in blue, if you notice, are coming much closer in line with the horizontal line than the red stuff that's kind of being derived manually using standard means. So we're able to perform much better calculating and imputing the core values. Believe it or not, these are missing from a lot of data for loans. It's loan-to-value ratio and debt-to-income ratio. The AML use case is very interesting. We're able to produce really great results again, and just to give you a sense for what we're able to do and how the kind of the use cases worked was we're able to identify to ingest all the know your customer data. KYC, for anybody who doesn't know banking, it's just know your customer. These are all, I call it KISS, but all the kind of funny acronyms that the industry has developed. But having the entity information, the communications, IP addresses, transactions from wires, etc., and all the high-risk lists. This is all unstructured stuff. If you really think about it, just a lot of text and lists of things. This is all structured data with some unstructured stuff, but also, most importantly, a lot of the kind of graph things, who talked to whom and who did something with whom. This is just IP address stuff. And again, just to give you a sense for what some of the hyperscalers are doing, Google is using the same vector tech for its search engine today. So search used to be rules-based and IP address-based, where the rules were specifically derived on that. Today, it's all probabilistic. And then we drive that to kind of behavior anomalies in kind of chapter 2, where we detect bad actors and are able to act on that. And then, of course, alert the right authorities and produce the reports. This is the example that I used earlier, which was the customer interaction distillation. And the real value there that we're able to do is, imagine you put in a business outcome. This is for a collection call, right? So, and the interesting part about a collection call is this is a person who is saying, hey, I'm calling in. I'm calling the bank, and I'm saying, I lost my job, but I got a new job, and I'm going to be able to pay you, but I'm going to be late. Well, we're able to immediately understand the intent of that caller in 2 interactions versus 20, just like I mentioned before, and quantify that so that this can be done to really improve and can give ops AI. As one of our colleagues was saying earlier, it's a big deal to operationalize, kind of to operationalize and really improve the ops side of the house. But this is kind of the ops AI example on the transactions. We can also do sentiment on voice as the caller is calling in, and identify if somebody's angry or happy or sad, and kind of act accordingly.
And Peter, it's worthwhile to mention that you can nudge the conversation. It's for the chatbot or.
So one of the interesting use cases we have is that when a situation is such that you can kind of influence somebody and you have their service records or other things. We did this with a very large cable company, for example. Nobody likes cable companies, but this is what it is. But to be able to then influence the discussion and kind of nudge it in the right way so that customer becomes loyal for life is where the opportunity is when things are quantified. This is a little bit of the example with the kind of transactions learning, where normally you get this kind of a transaction, and wouldn't be nice to get from this a view of the whole thing, where on the left-hand side, this kind of, the counting view or the classic analytical view can tell you the basket size, frequency, and all those things. What we can tell you is what kind of customer is that? And more importantly, what should we do with that customer from a decision perspective to improve on, where they need to be, right? That's kind of a little bit of a flavor of that. Last but not least, we said that we can do this at scale with all the global things. We did something for a very large media company where we basically gave them a better way to view the world than Nielsen was able to give them in terms of where to place advertisements and how to drive their value for the kind of audience they needed. Again, processing all the social signals from a lot of social sources, Twitter, Facebook, and YouTube. So that you can do these kind of things. You can say, hey, I want to advertise on this particular show versus kind of the other one, and so on. I think that's the background. I'm going to stop here, see if there's any questions. There's more slides we can post, and so on. Yes?
Peter, right, you said you applied this in the collections environment.
Yes.
So could you explain that a little bit?
So the collections, sure. So the collections use case, I'll come back to that real quick. So the collections use case was, the folks wanted to get very quickly to what the person what really wanted to do. And in this case, the business outcome they were able to specify here was let's grade a conversation, right? These were all live conversations that were going on. So this can be done like live in real time, right? So you have somebody talking, and this conversation is being graded, and there's two people talking. There is the customer, and there is an agent, right? And this view, all the way on the right-hand side, agent has like another way of being augmented and helping the customer in the conversation to get them to that outcome. But instead of doing it from, getting their name and all the other kind of information, we can get to the punchline very, very quickly and grade this to, hey, this whole conversation is actually highly quantified to meet the objective of this person is likely to pay, because we understood quickly that when they got a new job, they're going to pay. Because if you were just looking for any kind of automation that was looking for kind of text or word, a bag of words or anything else, it's very difficult to do that, because one of the things that's going to be there in a signal is going to be, I lost my job, which normally means I'm not going to be able to pay you. We can understand very quickly all that as it's going on and then quantify it.
Yeah, and that's because of the embedding that we discussed earlier. So imagine the business could, in raw text, say that it could be likely to pay, or likely to churn, or likely to cross-sell or upsell. So the business would specify what is the outcome that they're looking for in raw text. And effectively, the conversation is now graded in real time with respect to that given desired business outcome, so that the conversation could be nudged in the right way to get to that outcome.
Other questions? Yes, sir.
Could you give us an example of what the representation
Yes, sure.
mapped onto some big set?
Yes, sure. So supposing we are looking at a map, and the map has latitude and longitude. So those are the two coordinates for the city of New York. So you can then specify, give me the cities within a mile, within a 50-mile radius. Because you know the coordinates of the nearby cities, we can figure out who are the nearby cities with respect to New York. Okay? So now imagine we have the same problem, but instead of cities, we have customers. And for customers, for each associated customers, we not only have numbers, in which case it is easy to figure out who are the nearby customers, but we also have who the customer spoke with, who are the other interactions, what items did they buy, from which merchants, what text that they have published on social media or customer interactions. So all these records are going into this particular customer. But because these are not numbers, these are words, these could be images, text, it is not possible to like on a map saying, oh, give me latitude, longitude, I can figure out nearby cities. I can't do that. So this idea of learned vector embeddings transforms all of these disparate data into numbers, into number arrays. And now once everything is in numbers, we have a common backplane. And on this backplane, we can find distances. We can find similarities.
So a really kind of easy example that we use in language, in kind of vector space, would be what's up there for natural language processing. A vector space for human plus a vector space for robot makes a prediction and says, oh, it's just like a vector space for cyborg. We never taught it the concept, we never did any of that stuff, but it automatically gives you the answer. And it's very similar to that idea in, think of it in transaction space. That's kind of that's the aha.
So essentially, there's some kind of hash function that takes this piece of data
Yes.
and turns it into a numerical quantity that if you have two objects that are near in this vector space, they end up with this.
Yeah, it's like, look, you can think of it as locality sensitive hashing.
So it's funny. There are shortcuts, literally, so all puns intended, there are shortcuts that look at a lot of nonlinear stuff that deep learning does and everything else through hash-like functions. There's hashing shortcuts for some of the implementations without using GPUs for this kind of stuff.
Okay.
Right? VW is one, for example.
And
for
that
anyone.
mapping or hash function can be learned automatically.
That's
Yes,
right. That
that's
is
the
key.
big deal. Like,
That's
you don't
right.
have to be sitting there saying, oh, here's 1,000 pictures of cats, here's 1,000, or 1,000,000 pictures of cats, here's 1,000,000 pictures of dogs, now you can tell a difference. And then you got the wolf problem, right? It will learn it from your data. Most importantly, it'll learn it from your transactional data, right?
And so, for example, the likely to pay, that was the business, that was the desired business outcome. So I can do a keyword matching for the words likely to pay. I'll find some small subset. But if I can find in the semantic space of ideas and phrases that are nearby in the semantic space, then I have a much richer corpus, and I can make that connection. And if I can quantify that semantic distance, we are good.
Okay, thank you.
Sure. Any other questions? All right. Thank you very, very much. Cheers.